right. Good afternoon, and welcome to the prize ceremony. I'm going to just start right in on it. Our first prize is the Ivo and Renata Babuška Lecture Prize. This is the inaugural awarding of this prize. And the 2025 Ivo and Renata Babuška Prize is awarded to Omar Ghattas for his groundbreaking interdisciplinary contributions to the theory and algorithms of Bayesian inverse problems and their high-impact application across the geosciences. Professor Ghattas is a leading expert in computational science, applied mathematics, and high-performance computing, whose research focuses on large-scale inverse problems, uncertainty quantification, and PDE-constrained optimization. His work on developing numerical solutions for high-dimensional, complex systems has significantly advanced areas such as seismic inversion, earthquake and ice sheet modeling, and biomedical simulations. His highly interdisciplinary approach integrates advanced mathematical theory with practical applications in scientific and engineering domains, pushing the boundaries of high-performance computing and impacting widely used mathematical libraries and scientific application codes. Professor Ghattas is also deeply involved in integrating machine learning into scientific modeling to improve computational efficiency, making his work highly impactful across multiple disciplines. I can't think of many more people that would be as proud to give the inaugural award to than Omar Ghattas. So Omar Ghattas is going to present a lecture, but before he does that, I'm going to tell you a little bit more about him. Dr. Ghattas is professor of mechanical engineering at the University of Texas at Austin and holds the Fletcher Stuckey Pratt Chair in Engineering. He is also the director of the Optimization, Inverse Problems, Machine Learning, and Uncertainty for Complex Systems Center in the Odin Institute for Computational Engineering and Sciences, where he is a member of the faculty in the Computational Science, Engineering, and Mathematics Interdisciplinary PhD program. He also holds courtesy appointments in geological sciences, computer science, and biomedical engineering. Before moving to UT Austin in 2005, he spent 16 years on the faculty of Carnegie Mellon University. He holds BS, MS, and PhD degrees from Duke University. With collaborators, he received the ACM Gordon Bell Prize in 2003 for special achievement, and again in 2015 for scalability, and was finalist in 2008, 2010, and 2012. He received the 2019 SIAM Computational Science and Engineering Best Paper Prize and the 2019 SIAM Geoscience Career Prize. He's a fellow of SIAM and serves on the National Academy's Committee on Applied and Theoretical Statistics. He's director of the M2DT Center, a DOE ASCR-funded multi-institutional collaboration developing the mathematical foundations for digital twins, and serves as co-PI and chief scientist for Tax Frontera HPC system. All right, Omar?
Thank you, Karen. Thank you, Carol. Let me shake your hand. Okay. Thank you very much, Carol. Thank you to the prize committee and to all of you for coming and your interest in this work. It's a tremendous honor, and as Carol mentioned, this is the inaugural awarding of this prize. So it's really an honor of a lifetime, not just because Ivo's vision was that the prize recognize work at the intersection of algorithms, mathematics, computing, and applications. He really stressed that it has to include the applications. And therefore, it's a recognition of this entire community, the CS&E community, but also because Ivo spent the last 25 years of his career at the Odin Institute at UT Austin, and I overlapped with him for 20 years. And he was there, on a daily basis, pushing us and challenging us, and always asking, what kind of confidence do you have in the predictions of your models? What's the uncertainty? What's the reliability? And ultimately, will you sign the drawings? So he was constantly a thorn in our sides of the entire Odin community to push ourselves and to be more rigorous and be systematic about accounting for uncertainties. And that's what the inverse problem is all about. Before I talk about, I want to say a little bit more about Ivo, but before I do that, I want to recognize the people who actually did the work that I'm cited for, and that's the former PhD students, and I unfortunately don't have time to go through everyone, but I'll just mention a few names of people who are here, who have talks at this conference, George and Judy and Nick, and Amal, Toby, Jamie, Johan, the list goes on, Tom, Liang Hao, Josh, DC, Boyan, Sriram, Michael, Blake, Evan, Yuhang, Shindy, and then also research scientists and postdocs who contributed to this work, and many of them are here too, Karsten, Georg, Tan, Noemi, Melinda, Stefan, Umberto, Alan, Peng, Hussein, Harry, and then finally the collaborators themselves, Yusuf, Karen, Hannah, new collaborator, Mark, Bart, David, George, and Andrea's here, I think, and their students as well. Although I don't know if I should put Karen's picture here. If you talk to her, she says that the last collaboration we had, last paper we wrote, the Act in America paper, was likely the last paper we would ever write together. I don't know what she's talking about. You can ask her. Anyway, all right, and so finally, my family, my new family, Mira and little Z, who provide constant inspiration and joy. All right, so a few words about Ivo. He died the year before last and left a tremendous legacy. He was one of the founders of the mathematical theory of finite elements, made many fundamental contributions, if soup condition, Lagrange multipliers, HP methods and adaptivity, pollution, eigenvalue, error estimation, singularities, mesh, it just goes on and on. In his later years, he became very passionate about the need for reliability assessment and UQ, as I mentioned earlier, and he pioneered methods for verification validation. This was likely inspired by his experience as a civil engineer. He was a practicing civil engineer for a while. He did a PhD in civil engineering and then came back and did a PhD in mathematics and then went into his numerical analysis part of his career. But he'd always ask any seminar, those of you who gave seminars in the Odin Institute, Ivo would always sit in the front row, and you knew this, and he wouldn't let you get past the third slide. He was always asking, will you sign the blueprint? What reliability, what confidence do you have in the outputs of your model? So his final act, one of his final acts of generosity, established this prize and insisted that it recognize work at the intersection of these interdisciplinary areas. So we owe him quite a bit, and I'm very grateful. And as I said, it's the honor of a lifetime to receive this. So let me say a few words about the inverse problem, and then go on to a specific application, which is sort of the newest stuff that we're doing, and I'm very excited about it, and we'll share just a little bit about that. There won't be time to go into depth. But the inverse problems, and particularly their instantiation in the geosciences, which are a fantastic environment for inverse problems because geophysical phenomena are often characterized by complex, heterogeneous, multi-spatial scale, multi-temporal scale problems, and uncertainties in initial boundary conditions, constitutive parameters, source terms, closure models, et cetera. I refer to all of these as parameters. I overload the term parameter, but uncertainty arises in all of these aspects. At the same time, as the models have gotten better, the observational data have been rapidly expanding. Our ability to instrument, sense, and observe the Earth has been remarkable over the last several decades with satellites, with instruments, with subsurface measurements, and of course, sustained growth in high-performance computing. And all of these have come together, and very importantly, the mathematical and computational inverse theory treating infinite dimensional inverse problems, that has all come together over the last few decades, and this has allowed significant breakthroughs in the solution of inverse problems to occur and have opened the door to tackling even more challenging problems, and in particular the Bayesian perspective, which makes things much more complex, but is much richer and much more useful to actually making predictions. The SIAM Computational Science community has long been a fountain of inverse problems research. I counted just in this conference 40 symposia, 40 sessions on either inverse problems, data assimilation, or digital twins, which have the inverse problem as a fundamental component. And there are probably more buried under names like optimization and so on. So a little bit about the inverse problem, and I think I got this slide, I think from David Keyes. David, you were the first I've seen use this. I think it's a perfect picture, but you have the parameters, that's the cubes of meat here in the top. You have the forward model, which is the body of the grinder, and then you have the outputs, the observables, which are the ground meat. The forward problem is you turn the crank. You literally turn the crank and solve the problem. That's often, not always, but often well-posed, causal, and the operators are local. The inverse problem is the reverse. If I give you this ground meat, tell me what these cubes are that went into it. That problem is often ill-posed, often non-causal, and often global. The inverse operator couples solution values across all of space and time. So the classical way of approaching this problem is Tikhonov's approach, which tries to employ a judiciously chosen regularization to penalize unwanted solution features and guarantee a unique solution in the process. And one example of that is in this least squares form, where the parameter to observable map F deviates from the observations D, so there's a misfit penalty put on the misfit, and then there's a regularization term with regularization operator R that tries to penalize these unwanted solution features, such as magnitude, roughness, or expressing preferences for smooth solutions with jumps, or there are a variety of regularization methods. The Bayesian approach says, hold on, not so fast. There's a lot of information contained in this ill-posedness. There are many models that are consistent with the data up to the noise, and let's try to characterize them probabilistically. So the Bayesian approach tries to find all models that are consistent with the data and any prior knowledge through a posterior, so-called posterior distribution, the probability of the parameters given the data. In a special case of additive Gaussian noise and a Gaussian prior, the posterior takes this form. So the difficulty isn't writing the posterior down. The difficulty is what do you do with it, because it's a probability distribution in as many dimensions as you have parameters. The inverse problems that often arise in the geosciences have infinite dimensional fields as parameter fields. Once you discretize them, they can be million or billion dimensional. So what are you going to do there? How do you characterize a probability distribution in a billion dimensions? Just computing the mean alone is a challenge, higher moments. So this is the challenge. How do we explore this posterior probability distribution? Albert Tarantola, far ahead of his time, was a physicist who in the 80s made fundamental contributions to inverse problems, and particular geophysical inverse problems. And by the 90s, began to see the power of the Bayesian framework and began evangelizing for it. And if you know Albert, he truly was an evangelist. He was far ahead of his time. When he redid, or he updated his inverse problems book in 2005, I think it was, a SIAM book, he threw the deterministic inversion in the back, he brought the Bayesian to the front. The problem, though, is these twin challenges, which is the geophysical forward problems are highly complex. Anytime you sample the posterior, that's it. You've committed to going off and doing hours, days, supercomputer simulation just to compute the forward problem. So you touch the likelihood, and you're going to solve the forward problem. But moreover, you're in very high dimensions, 1 million dimensions, 1 billion dimensions. And now you're going to be evaluating the likelihood many times. So that quickly becomes intractable, and really the Bayesian framework was, there were people who were trying it in 1D and maybe simple 2D problems, but it remained really out of reach for decades. And Albert died 10 years ago or so, and never really got to see the fruition other than simple problems. Anyway, in the last 10 or 15 years, there have been a number of remarkable advances that are making Bayes more tractable. Advances in the theory of infinite dimensional inverse problems, advances in structure exploiting geometric sampling and variational measure transport methods, and advances in machine learning-based surrogates that can accelerate, of course, the whole sampling or variational transport methodology. So I'm going to share with you Okay, this is going to have to go fast. A few snapshots of large-scale inverse problems. This one is inverting for the friction in the basal friction in the Antarctic ice sheet from observations of the surface velocity. This one is earthquake global seismic inversion. This is poroelastic inversion, so from INSAR data, infer the permeability of a reservoir. This was a full Bayesian solution. The mesh was relatively coarse. It used geometric methods. These previous ones were based on Laplace approximation, made tractable with low-rank approximations of the parameter to invertible map, parameter observable map. And finally, this is ongoing work. You can hear more about it in Tom's talk in MS 120 on inverting for slip parameters and earth properties in subduction zone earthquakes from GPS instruments. This is accelerated by measure transport and neural operators. So in the last few minutes, I'll share with you this work. And obviously, I can't do it any justice, but please see Stefan Henneking's talk in MS 187 Wednesday afternoon, and Sriram Venkat's talk in MS 57 and 132. He's one of the finalists for the Bavarian Graduate School Prize. So that's, I think, the Tuesday morning talk. And we have collaborators, Alice Gabriel, UCSD, Melinda Fernando, and the MFEM team, some of them are here. I just saw Saniel Kolev is here. So this is a video just to show you the mechanics of subduction. So you have two plates that are being driven towards each other. They're locked, and suddenly the strain accumulates. The plates slide past each other. Massive earthquake is generated. Surface waves, so there's uplift in the sea in the seafloor that moves up the column of water, that generates surface waves, and they propagate as a tsunami. So that's what causes it. It's the seafloor uplift that is created by the slip on the fault. This is of particular interest to us in the Pacific Northwest, the Cascadia region, where the Juan de Fuca plate, which is a smaller plate here, oceanic plate, it's subducting underneath the North American plate, so roughly where my cursor is. And at the moment it's locked. The area that's locked is this pink shaded region here. So the plates are still being driven towards each other, but the friction is holding them in place. The strain is accumulating. There hasn't been an earthquake since 1700. It's not a question of when, it's not a question of if, it's a question of when. So sometime in the next, there's a 15% probability of a full magnitude 9 rupture along the full Cascadia fault in the next 50 years. That will unleash, massive tsunami up to 30 meters in height and significant ground motion, ground accelerations, and will cause significant damage. So the question is, can we invert in real time? So what are we going to invert? There's a plan to deploy seafloor pressure sensors through the Cascadia subduction zone, and this is one sketch of what it would look like. So these are pressure sensors, acoustic pressure sensors, and the idea is to make use of measurements like this, the transients right after, as the earthquake occurs, the seafloor is uplifted, acoustic waves are generated, use those measurements of those waves and go backwards and infer the seafloor motion. So once this seafloor motion as you saw over here, once that uplift is inferred in the inverse problem from measurements on the seafloor, then forward predict the resulting gravity waves on the surface, propagate them, and make predictions. We want to do this in a fraction of a second in order to be useful, because the first waves will hit in, let's say, 15 to 20 minutes. And we want to do this in real time, and we want to do it under uncertainty. The challenge now is that the forward problem has 10 to the 11th degrees of freedom. The seafloor motion, which is the parameter field we're inverting for, has 10 to the 10th degrees of freedom. As I said, we want to do this in real time, and we can't use surrogates. Hyperbolic problems don't lend themselves to surrogates due to this well-known Kolmogorov-Enwith problem. There's too much information contained in the data, so you can't come up with a low-dimensional representation. So how are we going to do this? The key idea is we exploit the linear time-invariant structure of the parameter to observable map So that is based on the idea that the forward problem is an autonomous dynamical system. It's shift invariant in time. The parameter to observable map inherits that structure. The shift invariance in time of the parameter to observable map implies that it's a block Toeplitz matrix, which can be diagonalized with FFTs. The FFTs, there's some offline work that's done. A number of adjoint wave propagation problems have to be solved, just equal to the number of sensors, not the number of sensors times time, just sensors. And then online, there's a rapid, fast computation that maps well into multi-GPU systems. Okay, so I'm going to skip the part about the forward model. It's acoustic waves coupled to gravity waves. And the inverse problem, I've already talked about the inverse problem. Just to say that a classical way, not even a classical, a state-of-the-art way of solving this problem would take 1 year. So if you want to solve this problem, you would take 1 year, and that's hopeless. 1 year, you need predictions within a few minutes. We said here seconds, but let's say you have a few minutes. And again, we can't do surrogates, no reduced models, no machine learning surrogates, because you're in 10 to the 9th parameter space, and there's too much information that's contained. Okay, so what do we do? Briefly, we exploit the fact, as I said, that it's a shift invariant system, and I'll skip over this material, and we have 4 phases to exploit this structure. There's 3 offline phases and 1 online. So the offline, that happens once, and we need fast adjoint solves. So we're building on MFEM here, and I'm going to show you some scaling results on the new LCAP system. And then there's some compact representation of uncertainties, which can be done offline because it's a linear Bayesian inverse problem, so the uncertainties can be pre-computed. And finally, the map point, the maximum a posteriori point, the mean of the prediction, that is the mean of the inversion. That can be done online rapidly. So here's some scaling results from the LCAP system. This has 44,000 AMD latest GPUs and a peak of 2.75 exaflops. So this is scaling, now this is strong scaling, and I'm going to show just the weak scaling. This is from 2 orders of magnitude increase in number of GPUs out to 43,000 with 92% parallel efficiency, up to 55 trillion unknowns. So this speaks to the system itself, the robustness, the system software, the MFEM library, and the wave propagation algorithms on top. So now I'm just going to go and show a couple of results, and then I'll stop. This is a very complicated bathymetry. This needs to be represented. This is the data. So what we did was we synthesized an earthquake. So we asked our seismologist collaborator, give us an earthquake that's plausible on the Cascadia fault. We haven't seen an earthquake since 1700, but tell us what it might look like. And this is what it looks like. On the left are displacements. So this is the vertical displacement of the seafloor. On the right is the velocity. The thing on the right, the field, the time-space field on the right, this is what we invert for. Okay? So then the next step is these are pressure waves on the left. So this is what the sensors are measuring. On the left is the pressure waves, and this is what the sensors are measuring. And on the right is the sea surface height. So this is the height of the sea surface. So this is what you forward predict. Okay? And now the inverse problem. Here's what this is the result that we get. Just a few numbers. We've got 325 million parameters, so not quite yet the several billion that the full Cascadia will involve. We have about half of Cascadia, but it's about 324 million inversion parameters, which is both space and time, because it's a time-dependent spatial field that we're inverting for. Total data dimension is 66,000, 2 billion degrees of freedom for the forward problem. This shows you very slow decay of eigenvalues. It doesn't admit low-rank representation. And then finally, this is the cost. So offline, we solve 275 adjoint wave equations. That takes 138 hours on each wave equation on 512 A100s on the Perlmutter system. And there's some very modest offline work in addition to set up what's needed for the inversion uncertainty quantification. And then online, it's less than a second to compute the map point and quantities of interest, which are the forward propagated So these are the forward propagated wave heights. So a total of 0.16 second to solve the inverse problem. You can see speedups there that are just massive. Again, this is exploiting the structure of the problem. And this finally shows the inversion. You can see this is the truth on the left. This is what our collaborator gave us, Alice. And on the right is what we inverted for. The sensor locations, you can see, we didn't have sensors in this upper left portion here, and that accounts for the noise. So the coverage was not complete. So we'll have to redo this with more complete sensors. And this is finally the prediction. So we'd like to forward predict with associated uncertainty where the surface waves are going. And what this shows you is that the black and the red, so the truth and the inferred, they all lie within the 95% credibility interval in all of these examples. Okay, so I better stop here. The summary, it was a quick talk anyway, so I think all of this is still in your head. And then finally, thanks to all the sponsors. Okay, I'll put it back there again. Thank you very much.
All right, are there any questions for Omar?
Thanks for the talk. I don't understand a lot about inverse problems. I just wanted to see what this was about. When you say that the problem is ill-posed, does that mean that potentially, if I'm thinking of x's as the inputs and y's as the outputs, does it mean that x1 and x2 could map to the same y?
That's absolutely right. That's right. It's surjective. It's not a one-to-one relationship. So there are many different x's that will give you the same observables, y, to, sorry, other way around. So there are many different parameters that, sets of parameters that can give you the same observables to within noise. And there's always going to be noise in the instruments, in the model, in prior knowledge.
And so how could you possibly know which one of them it was, just mathematically? Sure.
So the classical way of doing it is you regularize. You try to annihilate the null space of the inverse operator and select the one model, which really means sets of parameters. The one model is consistent with the data up to the noise that also satisfies some other conditions: smoothness, amplitude, smoothness plus a jump, whatever prior knowledge you can build in. The classical tries to get the unique solution. The Bayesian tries to characterize the whole posterior probability. So it's going to tell you, this is the probability of that particular set of parameters. This is the probability that's consistent with these data and this model and this prior knowledge.
Thank you.
But your intuition is exactly right.
Okay, in the interest of time, I think we're going to move on, but I just want to say one more time, congratulations, Omar.
Thank you, Carol. Thank you.